Good morning, everyone. For today's video, we're going to be taking a look back at set theory again, specifically answering the question of how do we count the number of subsets that a set has. What I mean by this is, say we had a set W, which was a set of the days of the week. Monday, Tuesday, Wednesday, Thursday, Friday. We want to know how many different subsets this set has. In other words, how many different ways can we break this set into pieces? Now, if you want like a sort of practical version of this question, an applied version of this question, you might say something like, well, you're trying to create a schedule for your classes. And you want to decide out of the options of taking classes Monday, Tuesday, Wednesday, Thursday, and Friday, which, if any of those days, you want to take classes for. Right? And each of those schedule decisions would be an example of a subset. So you might say something like, you want to take classes on Monday and only Monday. And this is a subset of W, right? If you decide just to take the set of Monday. You might decide that you want to take classes on Monday, Tuesday, and Wednesday, for example. And this is also a subset of W. Right, and there's tons of different combinations that you could come up with. You could do Monday, Wednesday, Friday. You could do Tuesday, Thursday. You could do every day of the week. You could even do no days of the week. Right? You could decide not to take classes at all. Now, that is a special case in particular called the empty set. Remember, the empty set is the set with no elements. So if you decided to take classes on no days of the week, we would represent that with the empty set. So the set with no elements. And symbolically, we write this to represent the empty set. But that's also an option considering this application as well. And so we could also say the empty set is a subset of W. And in fact, the empty set is a subset of every set. And that's going to be an important thing to remember here as well for how we can figure out the answer to this problem. Now, I should note here that there is a really nice answer to this question in terms of an explicit formula that will always be able to calculate the number of subsets based on the number of elements that set has. And I'm going to give you that formula, but we're going to save it to the end because I think more important than just being able to apply that formula itself is actually getting an understanding of why it is what it is and where it comes from. And so we're going to take a couple different approaches to get a feel for why that formula is what it is, and hopefully kind of, at least to start, discover it along the way. And so I'll tell you this much at least though, the number of subsets is going to be dependent on the size of the set itself. So the number of elements. So as you can see here, I've made out a table and we've got number of elements on the first column. We've got some examples. So for instance, a set with 0 elements would be the empty set. A set with 1 element would be like the set of the letter A. A set with 2 would be something like AB, right? And so on and so forth. We'll want to see if we can count the number of subsets, and what we'll find that's really nice is by counting these in the smaller cases, there's a nice pattern that we can then use to answer bigger questions as well. So the Monday, Tuesday, Wednesday, Thursday, Friday set, for instance, has 5 elements, and it would take us a pretty long while to count the number of subsets that it had just by listing them out. And this would get even more difficult as we made that set even larger. So if we took, for example, the set of all of the letters in the English alphabet, there's 26 of those. So counting all of the different ways that we could break that set into pieces would be an enormous task. And so in order for us to start to get a feel for what the pattern will be and ultimately figure out what this formula will be, we'll start small. We'll start with 0, 1, 2, 3, and 4, right? Sets that are manageable in size to work with very concretely. Let's see if we can play this game. If we have a set with 0 elements, right? An example being the empty set, how many subsets does that have? Like, let's list them out and let's count them up. The empty set, since it has no elements, really only has one subset, and it's the empty set itself, right? Because again, remember, the empty set is a subset of every set. But this would be the single example of a subset of the empty set. And so when we have a set with 0 elements, we're going to have one subset. Now, if we have one element, say the set A, well, we still have the empty set. That's a subset of every set. But now we also have the set A itself. That's also a subset. And these are the only possibilities. And so here we have two subsets of a set with one element. And we can keep playing this game, right? If we have the set AB, we have a few different options as far as subsets. We have the empty set, we have the set itself, AB, and we have the set of each of the individual elements. So the set A and the set B. And so that counts up to 4, right? And so here we have 4 elements. And we can keep going, right? A set with 3 elements is going to have the empty set. It's going to have A, B, C, the set itself. It'll have the set of each of the individuals, so A, and the set B, and the set C. It'll have also every possible pair. So we could pair A, B together. We could pair A, C together. And we could pair we could pair BC together. And if we count these up, we've got 1, 2, 3, 4, 5, 6, 7, 8. And so now that we've listed all the subsets, we count those to 8. We know that a set of size 3, a set with 3 elements, has 8 subsets. And we could even keep this going for 4. And now I'll fast forward this piece a little bit for you. But if you take the time to list these out, right, as I have here, and count these up, it turns out that we have 16 possible subsets. Now, hopefully at this point, you're looking at this column here on the right and saying, well, there looks like there's a little bit of a pattern there, right? If we go from 0 elements to 1 element, we're doubling. If we go from 1 element to 2 elements, we're doubling. From 2 to 3, we're doubling. From 3 to 4, we're doubling. And so each time, we are doubling the previous one. And that's really going to be useful to us because anytime we want to add an element to the set, what that tells us is we're doubling the number of possibilities of the set, right? And so from that, we can get this really nice explicit formula, which tells us for a set of size n elements, right? So n elements, there are 2 to the n subsets. And we can check that with what we just found, right? Because if we plug in some of these values, right, a set with 0 elements should have 2 to the 0, or 1 subset. A set with 1 element should have 2 to the 1, or 2 subsets. A set with 4 elements should have 2 to the 4, or 16 subsets. And so on and so forth, and everything in between. And when we check back with our table, that is in fact what we had, right? A set with 4 elements had 16 subsets. We counted them up. And so this formula will work for any size of a set. So, for example, if we go back to our set of weekdays, when W is equal to Monday, Tuesday, Wednesday, Thursday, and Friday, here we can count up and say, well, there are 5 elements, so there must be 2 to the 5th, or 32 subsets. So there's 32 different ways you could have rearranged your class schedule, for instance. And this will work for a set of any size, right? So even the letters of the alphabet, there's 26 of them, so there would be 2 to the 26 different ways that you could break that set into pieces. This is not the only way to think about this and get 2 to the n. Let's say we had a set A, B, C, D, E. We can also think about this by looking at each element individually. So for instance, let's start with A. If we are deciding to make a subset of this set A, B, C, D, E, and we look individually at the element A, we have 2 choices here. We can either choose to include it, right? So 1, we can include A, or 2, we can exclude A. And those are the only options in regards to that specific element. It either is going to end up in our subset or it's not. So for A, we have 2 options. For B, we also have 2 options. For C, we also have 2 options. For D, we also have 2 options. And for E, we also have 2 options. So at every point, for every element in this set, we have the option to either exclude or include A, exclude or include B, exclude or include C, and so on and so forth. If you're familiar at all with combinatorics, then you may know that when you take events in succession like this, you can multiply the number of options for each individual thing you are choosing to count the total number of possibilities in the end. And so we can multiply all of these 2's together, 2 times 2 times 2 times 2 times 2, or more specifically 2 to the 5th, to also count the number of subsets that exist. And that matches up with what we had before, because A, B, C, D, E has 5 elements, and we have now counted that there are 2 to the 5th subsets in a different way. So I hope you found this helpful. In the end, it does come down to the specific formula that the number of subsets is given by 2 to the n for n elements. But hopefully, at least one of those 2 ways give you at least some sense of where that comes from. So it's not just an arbitrary application of a formula. You're not just plugging in numbers, but there is actually a method behind that madness. There's actually a reason and a really nice picture as to where and why 2 to the n is what it is. Thank you for your question. I hope you found this helpful. If you have other questions, don't hesitate to put them in the comments below. I will be answering a lot of these in the next few days, next few weeks potentially. So yeah, keep the questions coming for sure. These have been great. Thank you guys again, and I hope you have a good rest of your day.